Welcome to Section 2, Deep Neural Networks. Last time, we looked at simple TensorFlow operations and using logistic regression on our font classification problem. In this section, we will dive into one of the most popular and successful machine learning approaches, neural networks. Using TensorFlow, we'll build both a simple and deep neural net to improve our model of the font classification problem. In our first video, we're going to review basics of neural networks. We're going to learn common ways to transform input data, understand how neural networks connect these transformations, and finally, how to implement a single neuron in TensorFlow. Our logistic regression model worked well enough, but was fundamentally linear in nature. Doubling the intensity of a pixel doubled its contribution to the score, but we might only really care if a pixel is above a certain threshold or put more weight on changes to small values. Linearity may not capture all the nuances of the problem. One way to handle this issue is to transform our input with a nonlinear function. Let's look at a simple example in TensorFlow. First, be sure to load the required modules and start an interactive session. Here, we create 3 5-long vectors of normal random numbers, truncated to keep them from being too extreme, with different centers. Note that because this is random, your values are probably going to be a little different, but that's perfectly fine. A common transformation is to square the input. Doing this makes larger values even more extreme, and of course makes everything positive. You can see the result here on the left. Conversely, if you need more nuance among your small values, you can try taking the natural, or any base, logarithm of your inputs. Check that out here. Note that large values tend to become squished together, while the smaller values are a little more spread out. But the logarithm can't handle negative inputs, and the closer you get to 0, the more extremely negative your small input becomes. Be careful with logarithms. Finally, there's the sigmoid transformation. Don't worry about the formula. Just know that extreme values, positive and negative, get squished to +1 or 0 respectively, and inputs closer to 0 become closer to 1/2. And here you see an example that's become close to 1/2. Started at 1/4 and is almost 1/2 now. In machine learning, we often call these transformations activation functions, and we usually combine weighted sums of inputs into them. When you consider the inputs, weights, and activation function, that's called a neuron because it's inspired by biological neurons. The details of how real neurons work in a physical brain is beyond the scope of this course. If you're interested in that, a neurobiology text might contain more. Or you can take a look at Gordon Shepard's Foundation of the Neuron Doctrine as one recent reference. Let's look at a simple example in TensorFlow. First, just create some constants, W1 and W2. We're going to multiply x1 by W1 and x2 by W2. Then we add these intermediate values and finally put the result through this sigmoid activation function with tf.sigmoid. Take a look at the result. Again, don't worry about the exact formula right now. You can have a variety of different activation functions. Just note that this is your first step towards your own neural network. So how do we go from a single neuron to a whole network? Easy. The input of one neuron just becomes the input for another neuron in the next layer of the network. Here, we've got a simple network with 2 inputs, x0 and x1, 2 outputs, y0 and y1, and 3 neurons in the middle. The value in x0 gets sent to each of the n neurons, but there's a different weight, the value multiplied with x0, associated with each. x1 is also sent to each neuron and has its own set of weights. For each neuron, we compute the weighted sum of inputs, put this through the activation function, and produce an intermediate output. Now, we do the same thing, but consider the neuron outputs to be the y's inputs. Note that by taking nonlinear activations of weighted sums of inputs, we effectively just compute a new set of features for our eventual model. Now we've learned the basics of nonlinear transformations in TensorFlow and what neural networks are. While they may not let you read minds, they are crucial for deep learning. In the next video, we're going to use a simple neural network to improve our classification algorithm.